Welcome back. In this video, I will discuss how to update weights in artificial neural network using a backpropagation algorithm with respect to bipolar activation function. In this case, we have been given artificial neural network with the three layers. X1 and X2 are the input layer neurons. Z1 and Z2 are the hidden layer neurons, and Y is the output layer neuron. We have been given input, that is -1 and +1. We need to propagate this particular input from input layer to output layer over here. And then we need to compare that particular output with respect to target output here. The target output given to us is 1 in this case. Along with this information, we have been given one more information, that is the learning rate. The learning rate in this case is equivalent to 0.25 over here. Also, we have been given the hidden layer weights. The hidden layer weights are these things, and these are the output layer weights over here. We have been written the same weights over here also. Now we will try to propagate this particular input from input layer to output layer. Before that, first we will try to understand what is the equation for bipolar sigmoidal activation function. The bipolar sigmoidal activation function f of x is given by 2 divided by 1 plus e raised to minus x minus 1. If you solve this particular thing, you will get the simplified version here, that is 1 minus e raised to minus x divided by 1 plus e raised to minus x over here. So whenever you want to calculate the output at any neuron, we need to use this particular activation function. But before you apply the activation function, first we need to calculate the net input over here. To calculate the net input, we can use this particular equation. Here the net input at Z1 is called as Z in 1. The net input at Z2 is called as Z in 2 over here. Now Z in 1, what is Z in 1? Z in 1 is equivalent to V01, that is the bias in this case, plus X1 multiplied by V11 plus X2 multiplied by V21 over here. So if you solve this particular equation, you will get minus 0.4 as the Z in 1. Similarly, we need to calculate Z in 2, that is nothing but the net input at second neuron. So how to calculate this one? That is calculated using this particular thing, that is the bias plus X1 V12 plus X2 V22. So once you put all the values and solve this, you will get 1.2 as Z in 2 in this case. Now once you know Z in 1 and Z in 2, that is the net input, you can apply the activation function so that you will get the output at this particular Z1 and Z2 over here. So the output at Z1 is equivalent to f of Z in 1, that is the sigmoidal bipolar sigmoidal activation function, which is equivalent to 1 minus e raised to Z in 1, 1 plus e raised to minus Z in 1 over here. So once you put that particular value and then solve it, you will get minus 0.1974 over here. Similarly, Z2 is equivalent to 0.537 over here. So we have calculated the output at Z1 and Z2. Now we need to propagate this as an input to this particular Y, and then we need to calculate the output over here. Now again we need to calculate Y in 1 or Y in, you can say. If you want to calculate Y in, we can use this particular equation, that is W0, that is bias, plus Z1 multiplied by W1, Z2 multiplied by W2. Once you put all the values over here and then solve it, you will get the Y in as, or the net input at Y is equivalent to minus 0.22526 over here. Once you calculate the net input, again we need to apply the activation function. Y is equivalent to, that is the output is equivalent to f of Y in, which is equivalent to 1 minus e raised to minus Y in divided by 1 plus e raised to minus Y in over here. The same value we need to put here. Once you solve it, you will get minus 0.1122 as the output here. So the final output is minus 0.1122 over here. But what is the actual output we have been given? The actual output is equivalent to 1 now. So this is not equivalent to 1. So what we need to do? We need to calculate the error term over here. So once you calculate the error term, we have to propagate that particular error backwards in backpropagation algorithm, and then we need to update this particular weights over here. Now the question comes in front of us is how to calculate error at this particular output neuron in this case. To calculate the error at the output layer, we use this particular equation, that is delta k is equivalent to tk minus yk multiplied by f dash of y in k. So what is k here? K is the output neuron number. So how many output neurons are there? Only one, so it will become 1 in this case. So delta 1 is equivalent to T1, that is the target, minus calculated value, that is y1, multiplied by f dash of y in 1, that is nothing but y in here. But the question is, what is f dash here? F dash of anything, that is f dash of x, can be calculated using this equation. What is that? Learning rate divided by 2 multiplied by 1 plus f of x multiplied by 1 minus f of x. So if you replace this x by y in, it will become something like this one, f dash of y in, which is equivalent to lambda divided by 2. What is lambda? Lambda is equivalent to 0.25 divided by 2, which has become 0.5 here. And this will become 1 plus f of y in, 1 minus f of y in. Again, what is this one, f of y in? F of y in we have already calculated in the previous slide. F of y in is nothing but minus 0.1122 over here. So put that particular value here, you will get this particular final answer. The final answer is 0.4937. That is nothing but f dash of y in here. So that we need to put in this particular equation. So delta k is equivalent to, or delta 1, because we have only one output neuron here. So delta 1 is equivalent to, what is given to us? Tk minus yk, t1 minus y1. So what is target? 1 minus, what is the calculated value of y here? We have already calculated, that is minus 0.1122 here. So this will become 1 plus 0.1122 multiplied by what? F dash of y in k, we have calculated that also here, that is 0.4937 over here. So once you put all those particular values, you will get delta 1 is equivalent to 0.5491. That is the error at this particular output neuron. So error at the output neuron is how much? 0.5491 in this case. Now once you calculate this particular error, using this particular error, we need to update this particular output layer weights over here. To update output layer weights, we need to know the change in weight. That is nothing but delta W1, delta W2, delta W0 here. What is delta W1 now? Delta W1 is equivalent to alpha, that is nothing but learning rate, multiplied by delta 1 multiplied by Z1 over here. So how much is alpha? Alpha is equivalent to 0.25. Delta 1 is how much? We have already calculated here, multiplied by Z1. Z1 is nothing but we have already calculated the output at Z1. So put those particular values, you will get delta W1, which is equivalent to minus 0.0271 here. Similarly, delta W2, in this case this Z1 is replaced with what? Z2. You will get the value as 0.0737 here. And delta W0, delta W0 is a bias here. Here we don't have any weights here, so it will be multiplied by 1. So alpha into delta 1 over here, you will get 0.1373. So we got a change in weights with respect to output neuron in this case. Now the question comes in front of us is how to calculate change in weights with respect to hidden layer weights here. That is delta V11, delta V21, delta V12, delta V22, and so on. To calculate these particular things, we need to know what is error at this particular neuron. We need to know what is error at this particular neuron, that is Z1 and Z2. Again, we cannot calculate error directly over here because this is the output layer neuron. We know the target, we can easily calculate the error here. But at Z1 and Z2, we don't know what is the target, so we cannot calculate the error directly over here. So what we need to do is we need to propagate the error what we have calculated at the output layer from output layer to hidden layers over here. To propagate that particular error, we use this particular equation, that is delta j. That is j, you can say that to z1 and z2. So for that one, delta 1 and delta 2 again. So that is equivalent to delta in j, that is uh, delta in j. I will tell you how to calculate later. F dash of z in j over here. F dash I have already told you how to calculate it. That is nothing but learning rate divided by 2 multiplied by 1 plus f of z in j, 1 minus f of z in j over here. That is quite easy. I will discuss it again at the later stage. But the question is, what is this one? This is nothing but because we don't know what is the error at this particular z1 and z2, we need to propagate this error backside. So we have already calculated the error here. So that error we need to propagate back. To propagate this one, we don't know how many number of output layer neurons are there. So right now we have only one, but sometimes we may be having one more here. So what we need to do is we need to propagate this error backside. So for that reason, we use this summation over here. That summation is I is equivalent to 1 to m. Here m is the number of output layer neurons. In this case we have only one, so this summation will go only one time here. multiplied by what? Delta k, that is a delta 1 here, that is the output layer error in this case, multiplied by this one is nothing but what? Associated weight here. So if you are propagating error from this layer to this layer, so you need to multiply this error term with respect to w1, you will get error over here. Similarly, if you want to propagate it this side, error is multiplied to w2, you will get error over here. So that is what the meaning of this delta in j over here. Because we have only one output layer neuron, this term, that is delta in j is equivalent to delta 1. This will become delta 1, wj1 over here. So because as I said earlier, we have only one output layer neurons, we will get this one. This summation term will be replaced with one time over here. Now we will try to calculate this delta in 1 and delta in 2, because this is delta in 1, this is delta in 2 over here. So delta in 1 is equivalent to delta 1 multiplied by w11, that is nothing but this weight over here. So delta 1 we have already calculated, that is the error at the output layer, and we know this particular weight is how much? 0.4 over here. So once you solve it, you will get this as the delta in 1. Similarly, delta in 2 is equivalent to the error we have already calculated multiplied by weight is how much? 0.1 over here. You will get this as the delta in 2 here. So now we have done with the first part of this particular equation, delta in 1, delta in 2 for delta 1 and delta 2 for these two particular neurons here. Now the final error term, how to calculate error term is delta 1 is equivalent to delta in 1, that is this term, the first term. We have already calculated it, multiplied by f dash of z in 1. F dash of z in 1 is equivalent to delta in 1, we have already written here. F dash of z in 1 is equivalent to alpha divided by 2. Alpha is how much? 0.25 divided by 2 is equivalent to 0.5 over here, multiplied by 1 plus f of z in 1 and 1 minus f of z in 1. So what is f of z in 1? F of z in 1 we have already calculated in the previous slide. If you just go back and see here, f of z in 1, you can see here the answer is minus 0.1974 over here. So this equation will become 1 plus 0.91974. Second time it will become 1 minus 0.1974 here. And once you solve it, you will get this as the error at this particular z1 in this case. Similarly, we need to calculate error at the z2 also. Delta 2 is equivalent to this term. First term is equivalent to delta in 2. We have already calculated. What is that value? 0.05491, that is the year, multiplied by this f dash term. F dash term is alpha divided by 2, that is nothing but 0.5, multiplied by 1 minus 0.537, 1 plus 0.537, that is nothing but 1 minus f of z in 2 here. F of z in 2 is how much? Z in 2 we have already calculated, that is equivalent to 0.537. So one time it will become minus 0.37, second time it will become plus 0.37, we will get 0.0195 over here. So we have calculated error at this particular z1, error at this particular z2. Once you calculate error, we can calculate the delta term over here, that is delta v11 is equivalent to alpha, that is learning rate, multiplied by error, whatever error we have calculated here, that is delta 1, multiplied by input is equivalent to how much in this case? Minus 1 over here. So once you solve it, you will get this one. Similarly, we will calculate delta 21, delta 01, this one, delta 01, for this one input is 1 over here. So alpha multiplied by delta 1 is enough here. Similarly, we have to calculate the other delta terms. Once you calculate the delta terms, we need to add these particular delta terms to the previous weights so that you will get the new weights. That is V11 new is equivalent to the V11 old, whatever the old weight is there, and the modified weights or the change in weight, you will get the new weight over here. The same thing is done for all weights so that you will be able to get the modified or the updated weights over here. So in this video, I have discussed how to use backpropagation algorithm to update the weights in artificial neural network with respect to bipolar activation function. I hope the concept is clear. If you like the video, do like and share with your friends. Press the subscribe button for more videos. Press the bell icon for regular updates. Thank you for watching.